Authenticity, as a classic security goal of cryptography, is demanding that within a system providing authenticity, the source of information can be verified by a receiving party. Very often, and with this course on the transport layer security protocol TLS a very prominent use case, this security goal of authenticity is often demanded within an online setup where a sender and receiver, such as a client and a server, are both online and interactively exchanging information. If authenticity is provided to the information exchanged, then the server receiving information from a client can verify that the information reaching the server was indeed sent by the client. The primary concepts of cryptography that can be used for providing authenticity to information exchanged are message authentication codes, authenticated encryption, and authenticated encryption with associated data. And as each of these three concepts is of importance to TLS, we will now have a more detailed look at each of them. Message authentication codes as the first cryptographic concepts serving authenticity are systems where the state of information is captured in something known as a MAC tag, and with these MAC tags calculated based on the information and a symmetric key K. The integrity of the information can then be verified later on by recalculating the MAC tag under the same symmetric key K. Let's have a look at the flowchart on the left side of the slide to see how this works. The prerequisite to using a message authentication code is to have a symmetric key K that is created and used for the purpose of calculating message authentication code tags. If we now assume to have such a symmetric key K, we can then take our plaintext and together with the symmetric key K trigger a MAC calculation which will result in a MAC tag. The plaintext together with the MAC tag could then be stored or sent to the receiving party that owns a copy of the symmetric key K. The receiver can then verify the integrity of the plaintext by recalculating the MAC tag with the same symmetric key, and if the recalculated MAC tag is the same as the MAC tag received, the receiving party can conclude that the plaintext received is correct and complete, and as such is in the same state as when the plaintext was sent by the sender. If either the MAC tag associated with the plaintext is wrong, or the plaintext changed in the meantime, maliciously or not, or a wrong key was used to calculate or verify the MAC tag, the MAC verification process would fail. A popular implementation of message authentication codes are hash-based message authentication codes, in short HMACs. HMACs were designed having the hash functions MD5, SHA-1 and SHA-2 in mind, which are three hash functions internally built according to the same principles. SHA-3 is internally built very different than MD5, SHA-1 and SHA-2, and as such, SHA-3 specifically doesn't apply to HMAC as a construction. Due to the increasing general insecurity of MD5 and SHA-1, it's nowadays recommended that HMAC is only used with SHA-2 as the underlying cryptographic hash function. Authenticated encryption as a second cryptographic concept to provide authenticity to information is now a concept that simultaneously provides authenticity as well as confidentiality to data. What is shown here on the left of this slide is the flowchart for a system known as Encrypt-then-MAC. This is a system combining primitives providing confidentiality with primitives providing authenticity, and as such, using this Encrypt-then-MAC approach requires as a prerequisite to using it two symmetric keys K1 and K2 to have been agreed on by both Alice, the sender of the data, and Bob, the receiver of the data, to be used for the encryption of the data and the MAC calculation on the data. Alice, as the sender of a plaintext, then in a first step takes the symmetric key K1 that she agreed on with Bob to use for the encryption, and with this symmetric key K1, Alice then encrypts the plaintext into a ciphertext by making use of an asymmetric encryption cipher such as AES. Alice then, as a second step, takes the resulting ciphertext and the symmetric key K2 and calculates a MAC tag, now not of the plaintext itself, but of the ciphertext. Alice then sends both the ciphertext as well as the MAC tag of the ciphertext to Bob. Bob, as the recipient, then receives something that up until that point he hasn't verified for authenticity and thus assumes that what he receives is just some ciphertext and some MAC tag. Bob then, in a first step, takes the ciphertext received as well as the symmetric key K2 he agreed on with Alice to use for the MAC calculation and calculates a MAC of the ciphertext he received. If the MAC tag he calculated himself matches the MAC tag he received, Bob assumes that the ciphertext obtained is really a ciphertext sent by Alice and proceeds into decrypting the received ciphertext by making use of the symmetric key K1 to recover the original plaintext that Alice sent. As we can see, this Encrypt-then-MAC approach now really is an authenticated encryption approach, as the plaintext is kept confidential by encrypting it before transmission, and that the ciphertext comes together with a MAC tag that authenticates the ciphertext with respect to a key that was agreed on by the sender and the recipient. Besides this Encrypt-then-MAC approach, other approaches to authenticated encryption exist. A second approach to authenticated encryption is the MAC-then-encrypt approach, which, as the name indicates, works exactly the other way around than the Encrypt-then-MAC approach by first authenticating a plaintext and then encrypting the pair of a plaintext and MAC tag. A third approach to authenticated encryption is then an approach called Encrypt-and-MAC, which encrypts the plaintext and which, side by side to this, also calculates a MAC tag on the plaintext. For more details on these two additional approaches, please consult the references provided on this slide. For us, at this point, all we need to know is that among the three approaches to authenticated encryption, Encrypt-then-MAC is the most secure and most recommended approach. Although a sound approach to authenticated encryption, this Encrypt-then-MAC approach has the downside of being cumbersome to use due to the many keys involved and due to the overall approach essentially just being a layered approach providing both the required security goals of confidentiality and authenticity, where it takes conditional logic to unwrap the layers again on the recipient's side. Let's have a look at an alternative that managed to improve on the Encrypt-then-MAC approach. Authenticated encryption with associated data is authenticated encryption that additionally binds the ciphertext to associated data. This associated data can be understood as the context that the data lives in and could, for example, be a TLS session or header fields of a data package where the payload of the data package itself is then encrypted. Authenticated encryption with associated data is now provided by various block cipher modes of operation, with two of the most famous and widespread authenticated encryption with associated data block cipher modes of operation being the Galois counter mode GCM and the counter with CBC MAC mode CCM. On the left side, a flowchart is provided that sketches how the Galois counter mode roughly operates and manages to provide confidentiality as well as authenticity to data with just one symmetric key instead of multiple symmetric keys like the Encrypt-then-MAC approach requires. Additionally, This Galois counter mode combines confidentiality with authenticity in just one pass instead of the layered approach that a straightforward implementation of Encrypt-then-MAC would require. On the encryption side, the Galois counter mode is essentially just a counter mode starting with an IV and then turning this IV into a counter that's encrypted with AES to form the ciphertext. This ciphertext then flows into what is essentially just a hash calculation, and where the result is then again encrypted with a counter mode of operation. The result of this final encryption is then the authentication tag of the ciphertext. What now really turns this into an authenticated encryption with associated data approach is that the associated data, the context of the data so to say, flows into the calculation of the final authentication tag and as such manages to bind the data to the context living within the associated data. It's clear that this provides both confidentiality and authenticity to the data, that this works against a single symmetric key, and that this is not a layered approach but essentially a one-pass combination of confidentiality and authenticity, and as such manages to improve on the Encrypt-then-MAC approach, at least on two qualities. This improvement, for example, also explains why in the newest TLS 1.3 version that we will get to know shortly in this course, only AEAD primitives such as GCM and CCM are used, but authenticated encryption approaches such as Encrypt-then-MAC are no longer supported. More on this topic will follow shortly in this course, so stay tuned.